to conclude this lesson, we'll do a question so that we can test and see that what we have learned in this lesson, did we understand? So we'll do question 1 here. As usual, you would know by now that when we solve problems, we adopt the mindset that I can solve this problem, right? Now, this is our academic constitution. These are a set of rules that we're going to use when you solve problems. They guide us to be able to solve problems and give us the motivation to solve problems. Now, if you want to know more about this academic constitution, please click on the video and the link that will take you to the video where I explain this method in detail in terms of how to use it. Now, the first part there, the I that we have there, this I here stands for interpretation, right? So we have to interpret the question. Now let's go on and interpret the question. Now, we're saying here in question 1, a box is pushed with a force F. Let me get my highlighter. A box is pushed with a force F to the right along a horizontal rough surface with a 0.5 coefficient of friction, right? One thing that quickly comes to mind is when tackling this question is to choose my direction. I'll use the reference frame in this specific question to choose my direction, and I'll then put on my data down to say we have a force F that pushes the box in that direction, and the surfaces have a coefficient of friction which is, they told us that is a static coefficient of friction 0.5, right? Remember, it's a ratio, it doesn't have units, right? It's a ratio, it doesn't have units. Just to write this properly, right? Now they say the normal force exerted by the surface on the box is 100 newtons. So this means we have a normal force going up like that, which is equals to 100 newtons. So I'm gonna write that down to say our normal force. So let me use the symbol that we wrote on the notes there. Our normal force is equals to 100 newtons. Now, obviously, you can see already from the diagram that we have the static friction force. We have the static friction force versus the applied force, right? And the object does not move, right? Remember what we said on our discussions about the static friction force. Always when you see a problem like this, it means they've given you the maximum static friction force. It means if you apply any force bigger than this, the object will start moving, right? They'll never give you situations where we deal with the static friction force being less than this formula, right? We'll always work with the one that is equal to the maximum. So this means that you can only work with the ones that are less if they give you that graph, or you have to interpret the graph or answer some questions on the graph, right? But for calculations, unless if they tell you, it will always be the maximum static friction force, right? So that is part of us really interpreting the question and also classifying this problem. I think also already I've classified this problem as I went through this process to say this would be a problem that will require me to perhaps use the formula for static friction force, because they've given me the coefficient of static friction force, they've given me the normal force. It looks like a problem that works with friction, right? And indeed, if you go to question 1.1, you then realize that they ask you to calculate the static friction force. They say calculate the static friction force. So we use a formula for the static friction force. Look at that, I wrote kinetic friction force. So we use the formula for the static friction force. This will be the maximum static friction force times the normal force. Now we do have these values. This problem becomes a simple substitution problem, right? So this is half of 100, which should be 50 newtons. Remember what we said, we don't report direction with this formula because it only measures the magnitude, right? So we then go on. Another thing is that, of course, this answer, if you navigate, so actually we have moved already. Now I'm not applying my academic constitution. We have moved to answer. That's why we did the answer there to get 50 by applying the equation. Now I want to navigate this problem. If I navigate this problem, I'll look at my answer. Does it make sense? Yes, it does, because we're multiplying our surface. The roughness of our surface is half of that. It's a reasonable answer. It makes sense, right? It makes sense, and it's not something that's too small or too big for a frictional force, right? The other thing that we can do is to change parameters and see how this number will change. If we change one of these, how these numbers will change. And actually in this question, they're doing that. They're telling us then now, when we continue in the question, to say the force F is increased. Look at this. They change parameters. They say the force F is increased, right? And the box begins to slide, right? Obviously, as we know, this was the maximum static friction force here. So if you increase this force, the box will start moving, right? But now, how will our answer change the previous answer that we had? Right? That's a very important question that we need to see. And the way our answer should change should be in line with what we expect, right? Because if it's not in line with what we expect, then that would mean our answer here of 50 Newton, maybe it's wrong. That's another step in terms of navigation, right? Looking at your answer, they say here now the coefficient of static friction. They say the coefficient of static friction, well, it's not static, but the coefficient of kinetic friction is 0.03. So they give us here additional data to say now the box is moving, then we have kinetic friction force, but now the kinetic friction force is 0.03. Now you'd notice here that this coefficient of friction has reduced, right? That's why even on the diagram here, when you look at the diagram, you will see that it is smaller, and this links to the kinetic friction force is smaller. Remember that the kinetic friction force is directly proportional to the coefficient of kinetic friction force. They're directly proportional. If the coefficient of friction decreases, right? If the coefficient of friction decreases, our friction also should decrease. The bigger friction that we had here should also get smaller. And we expect this as we were looking at a scenario where we were increasing our applied force and looking at how the static friction force increases well until it gets to a maximum. And then when the object moves, how the kinetic friction force gets smaller. Right, we expect this. We know this from studying frictional force in this lesson. Right now, here we then go and answer the question. So if you check, I went back to actually interpret, classify, and analyze this equation again, so that we can it's a loop now effect, so that we can navigate the answer that we got in 1.1. They say here, calculate the kinetic friction force applied to the surface of the box. So what is the kinetic frictional force that is applied to the box? Now there are two ways in which you can do this. One of the ways is that you can determine the ratio, the amount by which this force, the coefficient of friction has decreased, because we started with a static friction force, right? And then we ended up with a kinetic friction force. So to get how it has reduced, we can divide the two, right? To say our static friction force was 0.5 and our coefficient of kinetic friction force is 0.3. Then we can pull a calculator quickly there to say 0.5 divided by 0.03, right? This gives us 16.67. Remember that this is a ratio that we're looking for. It doesn't have units. So this is the amount by which our static friction force dropped to give us the kinetic friction force, the amount that because you can see that we started off with 0.5 and now we are at at 0.03, right? So this means now that, remember, we know that friction is directly proportional, right, to coefficient of friction. So if we apply it to kinetic friction, because we're looking for that, we should get the fact that our coefficient of friction has dropped, right? Also, our static friction force, our kinetic friction force, we expect it to drop, right? So that means we can take the 50 that we had for static friction force and multiply it by 1 over 16.67. We drop it because we want it to be smaller. So now this would be that answer times 50. Okay, I don't know what I did there, but we can say 16.67 multiplied by, oh, I see, I'm typing it incorrectly. So we have 50 times 1 over 16.67. So that we get here 2.3, no, I'm already getting to the answer because I'm rounding off already. Remember, we're going to have 2.1.999 now. But remember, we said our final answer should be reported in 2 decimal places. And in this case, actually, it will be reported in 1 decimal place because the 9 would make this to be a 10, and then we throw a 1 here, we'll have to get a 3 newtons, right? So that's one way in which you can do this. Another way in which this problem can be done, and I think this is the simplest one, I just wanted to show you how the friction force will change, right, in terms of the ratios. Now sometimes you can use the formula directly to say the kinetic friction force is equal to mu k times normal force, and we are given our kinetic friction force, and we also know that the normal force hasn't changed. And if you punch this on the calculator, you should get the same answer as we did in the previous one. We get 3 newtons directly. And again, remember that we don't report direction when we use this equation because it only accounts for the magnitude. We put in the magnitude of the normal force. I mean, these forces, we said they are perpendicular to each other, right? The normal force will be going in that direction and the friction will be going in that direction. They make a 90-degree angle. You can't determine direction in such a case. So this formula only determines the magnitude of these 2 forces. So this is how you will tackle this answer. And of course, our answer, if I navigate them, they make sense because now here we expect this force to have reduced compared to when it was static friction force. And we know from our theory as well that we said the kinetic friction force is always less than the maximum static frictional force. And remember, we said Fs here is the maximum static friction force, right? Guys, thank you so much for being with me in lesson 2 of Newton's laws as we're paving the foundation and putting our foundation together to be able to solve much more complex problems. Please stay tuned for the next lesson, which is lesson 3, where we'll be looking at the non-contact forces, right? So we have discussed all the contact forces that we have. Now we'll look at the non-contact forces. Please, if you are new to the channel, feel free to subscribe. It gives me a thumbs up. I would appreciate also if you can put comments and also email us on our email here, thescienceless at outlook.com. thescienceless@outlook.com. If you have any questions that you'd like me to do and share with everyone, or if maybe there's a topic that is difficult for you and you'd like me to break it down for you, right? Ladies and gentlemen, see you in the next lesson. May the force be with you.